So in chapter 13, we have solutions. We're going to be learning about different solutions and solubility and how solutions are made. Now, solutions are the mixing of two different things, as we know, and they involve two parts: solvent and solute. So the solvent is whatever the solute is dissolved into. Now, in a lot of aqueous solutions, which usually aqueous means in water, you're going to have water as the solvent. And in a lot of not aqueous or non-polar or organic solvents, you have either aqueous or organic. Organic solvents, there is a plethora of different solvents. There's even solvents that can dissolve both aqueous and organic things, non-polar and polar. They're kind of in the middle. They're half polar, half non-polar. And examples of those would be dimethyl sulfoxide. That's a really good one. Or benzoic acid. Some other organic acids are good at that too. But I mean, dimethyl sulfoxide, otherwise known as DMSO, is a really good one that can dissolve a lot of different things. It can dissolve ions, and it can dissolve different organic molecules. So, but anyway, you have the solvent and the solute. Now, solubility. Solubility, which we know the solubility rules, we know how to tell if something is soluble, but what exactly does that mean? So when one substance dissolves in another, it's said to be soluble. So this statement, I don't like this statement. Salt is soluble in water. Well, we know a lot better than this, because some of the salts that are the ionic salts that are in our solubility rules, we know are not soluble, such as magnesium hydroxide is very weakly soluble. Calcium hydroxide is weakly soluble. Silver chloride is not soluble at all. And there's more, or lead chloride, for example. Those are not soluble. So most salts are soluble. And then when a substance does not dissolve, it's insoluble. So you have oil and water, or any of these exceptions that don't follow the solubility, or that are insoluble on the solubility rules. Those are considered to be insoluble in water. But just because something's insoluble in water doesn't mean it's insoluble in other things. So when you say soluble versus insoluble, we have to be specific on what type of solvent we're talking about, whether it's an aqueous solvent or an organic solvent. Sometimes, and I'm learning this too based on my research, is that even in some organic solvents, if you have an organic molecule, sometimes in one solvent, it doesn't like to dissolve at all. But in another one, it does. So you have to specify which solvent. That's the idea here. Now, solubility depends on two things: nature's tendency towards mixing. That basically just means, is it energetically favorable? Is the mixing energetically favorable? And then the most important thing, which determines the first thing, is the type of intermolecular attractive forces. They need to be the same, or they need to overlap a lot. And when they do, we call it they're miscible. So in this case that are for liquids, let's say you have DMSO in water, or alcohol in water, they are miscible, meaning they can mix with each other. So if you have, let's say, orange juice in water, they're miscible, right? Because they're both technically water-based. So that means miscible. And then you have immiscible. Immiscible means things that don't mix, like oil and water. They're immiscible. So what was I going to say before? Intermolecular forces. So one last thing about this: for them to be miscible, or them to be soluble in one solvent to be soluble in another, they need to have the same type of intermolecular forces. I'll write that down. What that means is, if you have water, you have to have something else that has either ionic or dipole interactions. Now, when it comes to polar things that are like water, they don't have to have dipole, or they don't have to have hydrogen bonds. Things or substances that have dipole, hydrogen bonds, ionic bonds, dipole ion, or any combination of things that involve partial or true charges, those will usually dissolve in one another. So water, for example, can dissolve benzoic acid, which has dipoles. It's not an ion, really. It has dipoles. Or it can dissolve NaCl, which has true ions. So the fact of this, And it could dissolve proteins, which has ions too, but even if it didn't, it would still be able to dissolve based on the dipoles. So anything that has a partial charge interaction or a complete ionic charge is most likely going to be soluble in water. And then things that have nonpolar bonds, such as nonpolar bonds, and then nonpolar intermolecular forces, such as London dispersion forces, those are going to be soluble in each other, but not soluble in water. Okay, then the definition of solubility, and this is a good definition, is a threshold. So what it is it's the maximum amount of a solute that can be dissolved in a given amount of solvent. That's the great definition. So usually the solubility threshold or limit is expressed as grams per milliliter or grams per liter, something like that. But really, that's it. And this is the maximum amount. So if you have a substance that has a solubility of 2 grams per liter, this means if you put in 3 grams, 2 of the grams will dissolve, 1 of them will be left over. If the solubility is 2 grams and you put in 1 gram, it'll dissolve. Then you put in another gram, it will still dissolve. At that point, we call the solution saturated. And then if you put in any more, it won't dissolve. So that's how that works for solubility. It's a threshold. And intermolecular forces, just to remind you from last time, you have dispersion forces between the nonpolar molecules, dipole-dipole between 2 that are more polar, hydrogen bond between the hydrogen and the very electronegative atom of another molecule, such as oxygen, nitrogen, chlorine. And then you have the ion dipole, which in this case, so if I had to highlight something, let's say, so these 3 are all mostly soluble in each other, but the dispersion force, even though it's there and everything, it's not strong enough to dissolve. It's not as strong enough of a charge-related force to allow water to dissolve them. And that's a really non-polar thing. So everything from here to the right is polar in some way. Big differences in electronegativity. So yeah, just to reiterate, likes dissolve likes. All right, now concentration. So the main way that we talk about concentration in chemistry is moles of solute per liter of solution. And that's very easy. I think they might give you the formula, but honestly, you need to memorize it. It's good to know for everything. You can do a lot of problems and figure out molarity. I'm surprised they leave molarity this far into the chapter. I mean, you've seen molarity before. At least you should have. I think so. Yeah. So you've seen molarity before. So you basically have the moles over the liters. That's basically it. And then one you haven't seen before is called molality. And it's kind of like if you had a lisp and you said molarity. You see molality. Someone who can't say their R's themselves says L's instead. I have a friend like that. Yeah, not to make fun of people. I mean, my speech wasn't very good either. I had problems saying S's growing up. And I went to speech in school. And I still can't say S's that well. But I digress. Molality is more used in like chemical manufacturing, and because you involve like big numbers where it's like you're using the moles of a solute and the kilograms of the solvent. So if you're dealing with milliliters or microliters of solvent, you don't really want to use molality. So if you have big drums that are 10, 100 kilograms, then you might want to use molality to describe your concentration. And the thing is, it doesn't vary with temperature. So it's based on mass. Now, where the molarity is based on temperature. So if you're doing chemical processes, you're assuming you're changing the pressure or the temperature all the time, then the volume will change, right? Because if you're dealing with gases, especially, you're dealing with Boyle's law, Charles's law, Avogadro's law, all the different laws that we learned about. So your liters of solution will constantly be changing. So the amount of stuff you actually have, it'll be like, whoa, it's going all over the place. But molality is a constant. It'll be the moles of stuff you have in the vat, and then the kilograms of solvent that's in the vat. Those molecules will never change based on no matter what you do to that process, or no matter what you do with the temperature or the pressure. So that's why it's a really good way of telling concentration. And then you have mass percent. You've done this one before, I mean, at least in math or maybe physics. So mass percent, you have the mass of your solute divided by the total mass of the solution. And that's going to be your percent mass of the solute, right? And so you can figure out mass percent of really anything, and it's pretty easy to do. And then you have, off of that, you have mole fraction. Same exact concept, and we learned this before, that the mole fraction is the mole of one component divided by the total moles of all the components. So those are there are four main ways to tell concentration. So you have molarity, which is moles over liters. You have molality, which is moles over kilograms. You have percent mass, which is just the mass of one over the mass of the whole. And then you have mole fraction, which is the moles of one over the moles of the entire solution. So any questions on those four? Kind of just plug and chug. No? Good. All right. So then you have these things called colligative properties. So colligative properties are properties that depend on the amount of solute and concentration of a solution, not really what those substances are. So those involve vapor pressure depression, freezing point depression, boiling point elevation, and osmotic pressure. So the main three, I mean, vapor pressure depression is like keep that in the back burner. The main three that have equations to them that we can solve pretty easily are freezing point depression, boiling point elevation, and osmotic pressure. In simple terms, if you put a bunch of ions and increase the salt concentration of water, it depresses the freezing point and it elevates the boiling point. I'm about to say it boils the elevating point. So and also it changes the osmotic pressure because that's the concentration. All right. So here's what the new curves look like. So we saw these heat curves in chapter 12 where the temperature on the x-axis would change and the pressure on the y-axis can change. And then the pressure at a given temperature can directly change the state, or at any given temperature, a change in the pressure can definitely can directly change the state from solid to liquid to gas. So wait, Josh, I just saw your question. So it's not the raw number, it's the concentration. Wait for what? You could ask that. I'm not sure what you're referring to. This one? This one? Oh. Yes, they vary on concentration. Yeah. So, yeah, I mean, if you have more stuff in there, then it's going to change the freezing point even more. And it's based on molality. So it's, yeah. Yeah. Okay. So the first one is, well, let me show you this phase diagram again. Now, the pure solvent is shown in blue. And if you have a solution, meaning you mix a bunch of stuff in there, so maybe more than one solute, a bunch of solutes, a certain amount of solute, the phase diagram will shift. And it'll actually depress or decrease the freezing point, and it will increase the boiling point. So boiling point is from here to here. So it'll increase this here, and it will decrease the melting point. And we'll see the formula for that. So here is the formula for that. And I think you'll be given this formula, but it's pretty easy to know. And it is delta T, meaning the temperature change of the freezing point, equals the molality times the Kf, which is the freezing point depression constant. And that is that is solvent dependent. So if it's water, it's a certain number. If it's CO2, it's a certain number. So here's those numbers. The Kf for water is 1.86. Normal freezing point is 0. Normal boiling point is 100. And then Kb there's another factor called Kb that is the constant for the boiling point elevation. So those constants will be given, or you might have to figure out those constants with plug and chug and then put that into and look at a chart and see which substance it is. Yeah, and then M is the molality. So you would take molality times the freezing point depression constant. That would give you the delta T F. Now, it's not whatever you get for the, I see this mistake all the time, where a student would get this number for TF and then just write it down as your new freezing point. That's how much the freezing point decreases by. If it's negative, that means the freezing point increases, which usually wouldn't happen if you're putting more stuff in there. But if delta T, that means, let's say if it's not for water. Let's say it's for ethanol. The freezing point of ethanol is negative 114. If I got 4 for my freezing point depression number, this means it's negative 114 minus 4. So my new freezing point would be negative 118. So it's a change, is what I'm trying to say. Make sense? Okay, so we know that. Next is the boiling point elevation. Literally the same exact formula, but with boiling point. And it's elevated instead of depressed. So, and we have these constants called Kb. Really the same thing. So here's the formula. So molality times Kb equals your delta T. Now, same thing. If you went up to this chart and I said that we're doing a question for chloroform, which the boiling point is 61, and I get 5 for delta T, this means my new boiling point is 61 plus 5, which is 66, meaning boiling point elevation. Okay, the next one's osmosis, so osmotic pressure. Now, osmosis is, maybe you learned about this in bio when you were in high school, or if you're taking it now. So osmosis is the flow of solvent through a semi-permeable membrane from high concentration to low concentration. So this is how everything in the world moves. That's how wind is made, going from high pressure to low pressure. This is why things fall down rather than up. It's from high potential energy to low potential energy. So that's the key of life. Things go from high energy level to low energy level. True for electrons as well, as we know. But basically, osmosis has a pressure, and this is the amount of pressure to keep the flow moving, or keep the flow from taking, or the resistance to the flow. And it's called the osmotic pressure. If you increase the amount of stuff you have in there, the molality, that means you're going to increase the osmotic pressure, because you'll need more pressure to keep the water from not moving to the lower concentration. And there is a formula for this. And I'll show you a diagram of what I mean on the next slide. But the formula is this capital pi. Capital pi equals MRT. And look, R is back, our ideal gas constant. Oh, did the wrong thing. There we go. So our ideal gas constant is back. And M is the molarity. This time is not molality. Or yeah, it's the molarity. And then your temperature is in Kelvin. So whenever you have little m, like you do for boiling point elevation and freezing point depression, that's molality, little m. So I'll write m equals molality. Oh, that's wrong. It should be little m. And then big M equals molarity. Capital. So that's a good thing to know. Now let's look at osmotic pressure. So at first, initially, we have all the solute particles are on the left side. And naturally, what wants to happen is you have some osmotic pressure where the water molecules want to move from high concentration to low concentration in order to equilibrate the concentrations. So what they're going to do is if they go to the right, so they're going to go from high concentration of water. That's what I meant, not high concentration of solution. But it'll even out until they are equal concentrations, or at least they are as close as possible to equal concentration. Now, if we look at that, on the right side, we have 0 concentration on the left of the solute. On the left side, we have a bunch. So the water from the right is going to move to the left in order to dilute the left side as much as possible to be as close to the right side in concentration. To relieve that pressure, it will try to do that. But doing that will create a higher osmotic pressure, meaning the water level on one side will actually rise. And the pressure of the excess fluid pushing down is called the osmotic pressure, because initially there's no osmotic pressure. There's going to be a force, a gradient force that's pushing the water molecules through the membrane. But until there's an imbalance between the water on the left and right side, there's no actual osmotic, meaning water associated pressure, which happens over here. So you can actually do this and see it happen if you have a semi-permeable membrane. I mean, you can, it's like basically a filter, and like a small, like an osmotic filter. And then you put it in the middle of a tube. You put salt water on one end and then regular water on the other end, and you can actually see this happen. It might take a couple hours or overnight, but you'll see it happen. I think we did this in high school biology. We did an experiment like that. But yeah, another way you could relieve this pressure of this gradient is by moving the solutes across the membrane. But in this case, the membrane doesn't allow it. And at that point, it wouldn't be osmosis, it'd be diffusion. So diffusion is when you move the solute across the membrane in a semi-permeable membrane rather than the solvent. When the solvent's water, and then it's osmosis. Okay, any questions on that? No? All right. Next is the Van Hoff factor. So the Van Hoff factor is the ratio of moles of solute particles to moles of formula units dissolved. What does that mean? Honestly, that means the number of ions, or the number of ionizable things. The number of dipoles, I'll say a bunch of words. The number of dipoles, the number of ionizable things. So what does this mean? I'll give you examples. You can know this Van Hoff factor just from looking at a formula. Any non-electrolyte will have the Van Hoff factor of 1, meaning you'll have like a sugar. You can't ionize it and break it off into 2 parts. It'll just be 1 part. So you'll have an expected 1 per molecule. Then you have NaCl. NaCl has 2 ions. So when it breaks apart, you have a Van Hoff factor of 2, meaning 1 mole of NaCl makes 2 ionizable parts. MgSO4, it would also be 2, but it's not really close to 2 if you measure it, which is stupid. But yeah, this is what the definition of it is. I mean, the reason why it's measured differently is just because of energy, because you have a +2 and a -2, so it makes it a little different. There's a lot of different factors into play. And then you have MgCl2, which in that case you have 3 ions, Mg, Cl, and Cl. And then you have a Van Hoff factor of 3, and experimentally it'll be close to 3. Same for K2SO4, and for FeCl3 it would be 4. So it's basically the number of ions that can be taken out of an ionic compound. If you have taken out of a soluble compound. Sometimes you may not have any. You might have non-electrolytes. In that case, it would be 1. So why are we learning the Van Hoff factor? Oh, wait. Because we're going to use it. Oh, there's so much stuff here. Well, are we going to use it? We're going to use it. All right, the formula's not here. Fine. Guess you'll learn that. All right. So next thing is the vapor pressure of solutions. So the vapor pressure is the pressure above a solution. And what happens to the vapor pressure when you make a solution rather than just a solvent is the vapor pressure decreases compared to the vapor pressure of the pure solvent. So we talked about things like acetone last class, or like different organic solvents that have a very high vapor pressure, meaning it's very easy for them to come out of the liquid and form a gas. But then if you add a solution, add more things to it, things that kind of make it more rigid and increase the amount of intermolecular interactions, it'll keep some of those solute particles in, or some of those solvent particles in the solution, and that will decrease the vapor pressure. So that's how that works. And let's see, the pure solvent establishes a liquid vapor equilibrium. Addition of non-volatile solute reduces the rate of vaporization, decreasing the amount of vapor. Yes, it's basically the same concept. It's going to strengthen the liquid. Rayoult's law: the vapor pressure of a volatile solvent above the solution is equal to the mole fraction of the normal vapor pressure. So what that means is that you can tell the new vapor pressure based on the amount of moles with the mole concentration of the solvent, the mole fraction of the solvent. So basically what this means is if the mole fraction is 1, and this is the mole fraction of the solvent, not the solute. So if the mole fraction is 1, meaning the entire thing is pure solvent, the vapor pressure is going to be identical to the normal vapor pressure of that solvent. Once you start decreasing the mole fraction of the solvent, meaning you're increasing the mole fraction of the solute, you're going to have a corresponding decrease in the partial, or in the, I keep thinking partial pressure, decrease in the vapor pressure of the solution, of the solvent in the solution, because you're going to have more solutes in there that are making more interactions with the solvent, not allowing it to come out of solution as easy as if it was by itself. So does that make sense? If not, please ask a question. No? Okie dokie. Moving on. So according to Rayoult's law, the effect of solute or vapor pressure simply depends on the number of solute particles, right? So if you have a higher, this is why we talk about Van Hoff, and really you can read this, but the most important part is this part. So if you have a larger Van Hoff factor, that means you're going to have more moles of other things other than the solvent. So NaCl compared to sugar, you're going to have 2 moles of Na, 2 moles of Cl, or sorry, if there's 1 mole of NaCl, you're going to have 1 mole of Na, 1 mole of Cl. That's 2 moles total that's interacting with the solvent. If you had 1 mole of sugar, you're going to have only 1 mole of molecules. So the vapor pressure decrease with NaCl will be twice as much as for the sugar. And the reason why is because you're going to have twice as many molecules strengthening those interactions between the solvents and the solute, therefore lowering the vapor pressure, meaning the solvent will not want to be released into the air because it has more intermolecular forces. Okay. Basically the same thing, just firming up the concept. Any questions? No? All right. Cool. So here's the equations for that. We've seen this one already. And it works where the total pressure is the pressure of the solute plus the pressure of the solvent. If we're adding gases together or even liquids, you're going to have pressures, you're going to have vapor pressures of both the solvent and the solute. And then the total pressure is the vapor pressure of the solute plus the vapor pressure of the solvent. Of the solvent. So we talked about this already, really. Okay. So here's what a question would look like. Oh no, this is a mess. Put this over here. Cool. All right. So what is the vapor pressure of H2O when 0.102 moles of C8NO3 or calcium nitrate is mixed with 0.927 moles of water? All right. So first, find your mole fractions. So the mole fractions of ions versus the mole fraction of water. So the mole fraction of ions is going to be well, I mean, you don't have to figure it out for the calcium nitrate. You just figure it out for the water because that's how you're going to figure out the the new vapor pressure of the water. So you know that you have 0.927 moles of water. Now oh, Josh, this is the chapter 13 PowerPoint, but it's labeled chapter 14. I know. I'm sorry. But it was the old textbook had them switched and they never updated it. That's why. No, on Canvas, it's the topics. Go by the topics on Canvas. It's the topics that are underneath it are the ones we're learning now for chapter 13. Unless I flipped it, but either way, we're learning both chapters. So let's continue. Okay, so anyway, we're trying to figure out the mole fraction for water because we need to figure out how much the mole fraction is reduced from 1 to see how much the vapor pressure of the new solution decreased. Now, we know we have 0.927 moles of water, and now the moles total, because we know the mole fraction is moles of the substance divided by the total moles, it will be the moles of it in its dissociation. So don't think about it as just moles of CaNO3 too. Because in that case, oh, I just put 0.012 in there. No. When it's mixed with water, what's going to happen to it? We need our knowledge of electrolytes. We know it's going to dissociate into Ca2 plus and 2 ions of NO3. That's why an NO3 minus. That's why we have this written here. So we have 3 times the amount of moles. So that's going to be 0.306 plus the moles of the water. That's going to equal your total moles. Do this division, we get 0.752. Any questions on how I got the mole fraction for water or why we need it? No? All right. So next, we need to figure out the new vapor pressure. So we would simply just put the old vapor pressure of water, which the vapor pressure is going to be given, and it is given as, and it tells you right here, it's given as 118.1 torr, and we put 118.1 torr, our new mole fraction of 0.752, and that's going to equal 88.8 torr. So you see our new vapor pressure with the addition of solute of 3 moles of ions is going to be decreased by a pretty good amount, by 25%. Okay, any questions on that? No? All right. We're almost done. I mean, the rest of it is not that bad. So ideal versus non-ideal. It's not too important, really. Vapor pressure, but non-ideal. So, I mean, ideal, what do they say about non-ideal? So solute-solvent interactions are stronger. We know that already. So sometimes it could vary. Basically, sometimes it could vary off of that. Kind of like the ideal gas law. There is variations. So if you have some solutions that have a stronger solute-solvent interaction than the assumed in the Raoult's law, then it varies a bit. So if you have a weaker solute-solvent interaction, the vapor pressure will be higher of the solution. If you have a strong solute-solvent, the vapor pressure would be weaker. And this makes sense conceptually of what we talked about. Why is the solution vapor pressure decreasing in the first place? Because you're strengthening the solute-solvent interaction. But if you have an insanely strong solute-solvent interaction, the vapor pressure is going to decrease even more. But if you have a weaker solute-solvent interaction, the vapor pressure of the solution will be less. The decrease will be less than you originally thought. So in some cases, it might even increase if the solute-solvent kind of repel each other, which is possible. So I mean, there's just variations from that. Heat of hydration. So the energy added to overcome the water molecules released in forming attraction between the water molecules and ions. It's called the heat of. Okay, so basically, if you have a mole of, or if you have a solution, and you want to take away or if you want to, how do I explain this? So if you want to put water into solution, if you have a mole of molecules or mole of any type of salt, right? And you want to hydrate it, you have to add enough water to compete with the ionic bonds of the solute. This is called the heat of hydration. And normally there's heat associated with this. And you can see, or you can feel it actually. If you take, well, with NaCl, it would be very little. But if you take like magnesium sulfate or other kinds of salt, and you put a crap ton of water in it and then mix it really violently, and you feel the cup or the beaker, it'll get warm. That's the energy being released from the hydration of the salt. So the point of this is that's a thing. So when ions dissolve in water, they become hydrated, and they're each surrounded by water molecules, which we learned about. We learned about that. And then this really isn't too, I mean, we've kind of talked about this already. Lattice energy a bit. Yeah. Nothing else is really too pressing. Yeah. So next, solubility limit. All right. So this is, I did touch on this, but we'll talk about it more. So like I said, the solubility is a threshold, right? It's a threshold at the amount in grams or even moles, but usually grams or milligrams of solute that can dissolve in a specific amount of solvent. If it is at this point, meaning like, let's say it's 2 grams per, let's use this example. So you have 2 grams per milliliter equals solubility. Right, that's a lot. Let's say 0.5 grams per milliliter equals solubility. If you have 0.5 exactly, the solution is said to be saturated. So a solution that has a maximum amount of solute dissolved, it's saturated. It also depends. It depends on 3 things. It depends on the amount that can be physically dissolved. Depends on 3 things. The amount of solvent, obviously. If you have 2 milliliters, you can dissolve twice as much. The temperature. Usually, temperature increases the solubility. Usually, it increases the solubility of a salt. And the pressure of gases, if you have gases. So usually, if you decrease the pressure, or if you decrease the pressure, it decreases solubility. Increase the pressure, increases solubility, because it forces them physically to go together more. So now, if you have a theoretical solution that has 0.25 grams per milliliter, it's now unsaturated. So a solution that has less solute than the saturation is said to be unsaturated. Then you have, where you have more, we call it oversaturated or supersaturated, where you have, let's say you have 1 gram in 1 milliliter. What will happen is, so easy way to figure out solubility, you take a milliliter, or screw it, you take like 20 milliliters of water. You put in 100 grams of salt. 20 milliliters of water, 100 grams of salt. You mix it thoroughly. You take out, you put it through a filter. All the salt that is not dissolved will be in the filter. There will be dissolved salt still in the water. You let that go. You dry off the salt that's in the paper, in the filter paper. You dry it off really well, and then you weigh it. Let's say you start out with 100 grams. When you weigh it, you'll end up with 20 grams, or not 20 grams, like let's say 80 grams. That means you assume 20 of the grams were dissolved in the water. That means the solubility is 20 grams per 20 milliliters of the water, in the water. So that means it'll be 1 gram per milliliter. So that's one way you can figure out the solubility of any substance in any solvent. As you do that, you mix them up good, you super saturate it, and you see what's left over, and then you subtract. So that's just an idea. That's how this stuff can be applied. All right, so here are those solubility curves based on temperature. So with most things, if you increase the temperature, you increase the solubility. There's really, except for sodium sulfate, you increase the temperature, you decrease the solubility, but most of them is an increase. And why is it a decrease? I don't really know, honestly. It's just for that substance, it likes to do that. Then effective dissociation. So we talked about Van Hoff factor already. Adding, so here's what happened. This is called seeding. This is actually really cool. If you have a saturated solution or even super saturated, and it's very, you see it's very clear. It's very clear. There's not really anything, but you know it's at the limit. What we can do is we can seed it. So what seeding is you put in some of the raw solute, you put more of it in there, even though it's saturated. What will happen is, because it's saturated, it will force the molecules of the solute that are inside the water that are dissolved already to become undissolved and start to like precipitate, because it'll kind of like, we call that seeding, meaning it'll kind of seed the reaction to happen. It'll start it. It will provoke. And then what will happen is you'll have a crystallization event. And then you can have all the solid will crystallize. So that can happen. That's pretty cool. And then for gases, so for temperature, we're talking about pressure, but not temperature. So for all gases, the solubility decreases as the temperature increases. This makes sense because, oh, sorry, I didn't see your question. So it dissolves in the new solute and precipitate. It dissolves a new solute and the precipitate of the solute that was already, and precipitates the solute that's already, no. So when you put this solvent in, or the solute in, it'll be crystal already. It won't dissolve at all. It will just force the other solute particles that are dissolved to come out of solution, to precipitate. So that's called seeding. Yeah. Okay, so for gases, if you increase the temperature, you're speeding up the molecules. If you're speeding up the molecules, you're increasing their chances of interaction, but you're making them more volatile. They're bouncing off each other quicker. The solubility will generally decrease. Will decrease in this event, because you're going to have less chances of they're going to be hitting into each other, but less chances of real combination. So here's solubilities, I think in grams per liter, probably grams per milliliter of different gases at different temperatures. In something else. I don't know what they're in. I'm not sure, but you see as temperature increases, the solubility decreases for all of them. All right, so then we have pressure dependence of solubility in gas and water. So pressure. Now, once we increase the pressure, it increases the solubility of gases into liquid. And you can think about this as a Coke can. So in a Coke can, it's pressurized. What happens when you flip the pop tab? It fizzes, and all the carbonation comes out. Or when you have a seltzer water, you open it, it fizzes. Why does that happen? Because you have a pressurized headspace. This headspace right here, that's the air above the liquid, is pressurized. This pressure is keeping the gas molecules, or the CO2 that are in the carbonation, it's keeping them solubilized in the liquid. So in this case, for any carbonated beverage, you have dissolved gases, dissolved CO2 in liquid. Once the pressure is released and it gets put at equilibrium to atmospheric pressure, all of the CO2 is now, oh, I don't have to stay in the water. There's no pressure pushing me down. I can now be released. So the solubility, as soon as the pressure decreases, to the open air, the solubility decreases of the CO2 into the water. So that's how soda cans work. Any questions on that? Okay, one more thing. Henry's law. So Henry's law is the solubility of a gas. It tells you its solubility is directly proportional to the partial pressure. So if you have the solubility of a gas and you have this constant, which is the Henry's law constant for several gases in water, and this is for solubility in water. So for Coke and other drinks like that, it's water-based, so it'll be in water. And it'll be about the same constant. You can, based on its pressure, you can determine the solubility. So it's another directly proportional formula. And I mean, this would be given, I honestly don't think you're gonna have questions on this on the exam. It's a very small part of the lesson, but I mean, it's there. So you might have questions on the homework about it. Okay, don't worry about colloids too much. Colloids. Yeah, we're going to talk about solids more the next. Yeah, that's more physics stuff. We're not going to. So now, chapter 14, we'll talk more about solids and different types of crystallization and lattices and stuff. But okay, so that's about it. Any questions on Henry's law or really anything else? You guys were kind of quiet today.